Howdy. This is our MXET final project. My name is Abdul.
I'm Jonathan Burgess.
I'm Richie Digert.
I'm Moizuddin Shah.
And we're going to be talking about our metal detecting robot, Gerald.
Alright, so the concept for Gerald is that its primary function is to avoid obstacles, both dynamic and static. He moves in a straight direction until he senses an object with the LiDAR, and then he will turn left and right or right away from the wall depending on where it is. The secondary function for him is to detect metal objects in its path with the metal detector, which will light up an LED on the detector, log it in a file, and activate the buzzer. The scuttle uses a LiDAR for obstacle avoidance, the H-bridge on the motor to control the two back wheels of the robot, and a metal detector for detecting metal, and the BeagleBone Blue, obviously. The metal detector was placed on a mount as shown in the picture on the following slide and connected to the underside of the scuttle, so it had the highest likelihood of detecting metal objects. A DC splitter was also needed to power each of the components, and the LiDAR was mounted on the front along with the detector.
Here's a picture of our mounting bracket. This is what was used to mount the metal detector to our robot, which twisted into place. Use this design right here. Here's a picture of our buzzer setup. So the connections from metal detector down there to the breadboard and to the buzzer, and then they are fed back through the GPIO pins for the BeagleBone to read it. And this is a final picture of our design in place. It's the metal detector. It's twisted under the robot to protect it from anything around the robot. And something to note here is the space between the wheels. Can only detect right under the metal detector right here. So this void, if a metal passes by, it will not detect it.
So the main portion or the main driving force of the program was using multiprocessing in Python. So that way we would be able to run all of our scripts in parallel. So the multiprocessing or the scripts that we ran with multiprocessing was the voltage monitoring script for the battery pack of the robot, a script to pull the metal detector and get status, a script for the search pattern of the robot, and a script for obstacle avoidance. So the metal detector script worked by polling the GPIO pin of the that was connected to the metal detector via the breadboard. And if the metal detector detected metal, then it would send back a high, 1, that was read by the Python program. And if there was no metal detected, then it would just send back a 0 or a low, which was read as a 0 by the Python script. The movement script was just used to drive the motors forward while it was running, and that was integrated with the obstacle avoidance script, which pulled the LiDAR and determined if there was an obstacle within the threshold we had determined, which was about 30 centimeters, so 30 centimeters away from the frame. If there was an obstacle, then the obstacle avoidance script would take control of the motors, and it would turn the robot away from the obstacle and then continue moving forward. There was also a case included in the obstacle avoidance script for if there was a wall detected, so something directly in front of the robot, then it would turn 180 degrees and then resume its search pattern. And the final integration with the metal detector was that if the metal detector determined that there was metal found, then it would stop the motors and it would send a high to the buzzer so that there would be an audible signal for people to know that metal was detected, and then it would resume search pattern and obstacle avoidance again.
I'll go ahead and go over the demonstration. We can see the robot move towards the metal object, detected with the buzzer. Then it will detect the obstacle in front of it, turn all the way around, detect the wall, detect the side chairs, just avoiding everything around it, while running a random search pattern. Here we can see a little bit more of a dynamic obstacle using the stick to suddenly point it at it and stop it. You can see it avoids everything very well. The reason it's staying in one area is making sure it's scanning most of the area before it leaves it. You can see it slightly, oh, just detected another metal right there. Ideally the metal would not move, so it would not detect it more than once, but since this was a object on the ground, then it can detect it more than once. You can see it progressing slightly, going towards the other areas. Unfortunately, because of the size of the metal detector, if it goes over a metal from the sides, then it doesn't really detect it, as you can see right there. You can see it keeps progressing, and here's another metal detection. It is only programmed to stop 2 seconds above the metal and then keep going, since it is logging the data and telling the user. And this is the node red. From the user's perspective, for monitoring purposes, we can see that it says detect status, no metal found, and the vector and the distance of the nearest object.
Okay. So the way that the program integrated with the Node-RED GUI was that there were log files generated. So there were three, or actually it's four main log files that were generated. The first one was the voltage level of the battery. So that was sent to the Node-RED flow. The second one, the second two actually are the distance of the closest obstacle to the robot as detected by the LiDAR and the angle of that obstacle from the robot's local x-axis. And then the final log file was the one from the metal detecting script, which basically sent to the Node-RED GUI whether or not metal was found. So if there was metal found, then it printed on the Node-RED GUI that metal has been found. While there was no metal found, it printed that no metal has been found.
Even though we have finished working on the robot now, we do have ideas for if we were to continue working on it, how we would improve it. The main thing that we would want to do is get a higher quality metal detector, both in actual depth of how far it can detect and also the area in which it can detect metal, to make it less likely that it rolls over a piece of metal and doesn't actually detect it. Another improvement we would like to make is the actual mapping system that would be able to record the location of pieces of metal found and show them as a map for any human who wants to go and find those objects. Another potential improvement we were thinking about is better tires, better wheels for perhaps being able to take the scuttle to the beach, because as it is, the scuttle, we never actually tested this. We didn't get the chance to, but we very much doubt that it could run well on sand. And then also we want to do further localization on obstacle avoidance refinements. What we got worked for, demonstration purposes, but if we were to make a continued development, we want to refine this even more. As far as work distribution goes, we have a Bill who 3D printed them out He helped with the troubleshooting for the metal detector. He came up with the GPIO pin setup with buzzer, and also helped with the obstacle avoidance troubleshooting. Moyes came up with the obstacle avoidance program, also the multi-processing layout and software integration for the whole project. Richie helped with the PID control tuning. He also did troubleshooting with the obstacle avoidance and was also the lead for writing the report. I did the soldering and troubleshooting for the metal detector, and I also helped with obstacle avoidance. Thank you so much for listening to our report. We had a good time on this project, and we hope you enjoyed listening to it. Thanks, and gig 'em.